Right. Okay. So for the next few weeks, we're going to cover malware analysis. So this week, I'll give some of the basics around malware, and I'll hopefully give you an example of some real malware. But just now, we'll look at the basic principles of how we investigate. So over the next few weeks, you'll be looking at much more detail about how malware code is created, and then I'll be doing ransomware and a bit more in-depth analysis at the end of the module. So that'll be in about 3 weeks time. Okay, so the areas that I'm going to cover is to look at basic code, to understand what code really means. And the world of the Intel processor is going, and we're moving much more towards the ARM architecture. We'll have a look at a taxonomy. So I haven't really found a proper taxonomy yet that really articulates malware, but we'll try and see if we can find one that can describe it. Then we'll look at the basic classifications. Very difficult to classify. If you look on VirusShare, you'll probably find that a piece of malware is classified in many different ways and given many different names. So one person's ransomware is another person's backdoor, and so on. So it's difficult to actually define it properly. After that, we'll look at some static and dynamic analysis, look at some code analysis, try and understand how the machine level actually works, and then we'll look at a real exploit kit. The core to much of this is really to make sure that systems are patched properly. So you really can't beat, apart from an attack against 0 days, then the most ways that you can protect against malware is to patch systems. And the 3 pieces of malware that have been in the top 10 for many years and probably still are 2 Adobe products and a Java product. So the Java exploit, you can see, is 2013, and it's still used. Why do you think it's still prevalent? What's the problem with Java, do you think? That means it's still an exploit of choice. Was it? I haven't patched it, yeah. Yeah. So it's very difficult. It's not an easy process to update your Java. Your programs will typically bind to a certain version of Java. It's not like .NET, where you get many different versions of the framework on your machine, and whatever version the .NET program has been compiled for, it will run from that framework. So Java has a bit of a problem, and there are well-known exploits for it. The other two, obviously Flash has a very bad track record in terms of its security. Code can easily fall through the browser and right onto the machine, and they're still patching it. The first company to try and get rid of Flash, first major company, which company? Apple, yeah. So it was Apple that never much liked Flash and didn't support it on their machine for security reasons. There may be other reasons, but that was the main reason that they gave, that they couldn't trust Flash to run on a Mac. So generally, we'd be migrating away from it, but many sites still actually use it. And then there's the PDF vulnerability that we get. So if someone can send you a PDF as a backdoor in it, and it can exploit the machine. So these ones here are actually pre-compiled. So now we get what's called crime as a service, or malware as a service, and it's possible for an intruder to purchase an an exploit kit, and those exploit kits have ready-made vulnerabilities. You can even get a service contract with updates as required. As systems are patched, then it's possible to get updates for the vulnerabilities. So we'll have a look at an exploit kit a little bit later. But that's the three differentiations for code. So we go from a high level, human ready, into something that is machine ready. So we either use a compiler, an assembler, or an interpreter to take our high level code into an executable form. So examples here, C++, Fortran. C++ is still the top language used in industry, and it's still the one that causes most problems. So normally we take our compiler, we compile the object code, we bring in a static library, we link it together, and it produces the exe. Obviously that had a large overhead in actually building the exe. So increasingly what we do is we compile to DLL, and whenever the exe needs the DLL, it pulls it in as required, and then it can leave it. Obviously what can happen is that we can have an injection of a DLL, and that's what's called DLL hell. DLL hell is where somebody goes and replaces a well-known DLL with another one, especially a system one, and then they can actually create a backdoor within there. Okay, so that's the main process that we'd go through from there. But increasingly we're moving over here, and that we did this because of speed, but more and more we have very powerful computers, so we can interpret the language as we go along, and we don't have to compile it, we don't have to get it ready for the machine, and then all we need to do is install an interpreter. The interpreter will then take the code and interpret it for the machine that it's actually running on. So Python, Ruby, ASP, PHP, JavaScript, TCL, all are high-level interpreted codes. Can you give me another example of a high-level source code language? Was it?
You said compiled, right?
I compiled, yeah.
Go.
Go, yeah. Any other more popular ones? C, yeah. And then for a high level, any other ones? High level interpreter. So which one's going to be faster, the compiled version, or the interpreter? Compiled. Which one is going to be more robust to errors? Compiled, okay. So which one is going to be more compatible on systems? Interpreted, okay. So the interpreter is good now for producing code that can run on systems. So the other thing that we have is that we can if we want to analyze the code, then we can run a debugger on it, and then we can actually watch the code run. It's very difficult to stop the debugger, and as we'll find, obfuscators try to crash the debugger if it can, but it's often a race between the obfuscators and the debuggers. So you often have to update your debugger often to stop it from so it can still crash the system. Oops. And the other thing that we have is that if we have an exe, it's actually not too difficult to decompile a program back to the original source code. So again, what we need is strong obfuscation here. So obfuscation normally involves changing the names of the variables, so that it's very difficult for somebody to maintain the code. So even though they reverse it, then it's not possible for them to maintain the code. Also, you use encryption for the strings inside the code. Okay, so that's our basic steps that we take. So this is really the legacy way. So the legacy way is that we have a portable executable. It runs on the operating system and then directly onto the hardware. The problem that we have here is that the exe is interacting almost directly with the processor. It can cause a blue screen, it can hog resources, and so on. And then increasingly, well, started by Java, what we have is that we run our programs within our framework. So with this, we create an intermediate level code, which is pretty near the machine level as an abstract point of view, but not exactly. So the overhead of converting this into machine code isn't too difficult, and it's almost there. So we go from our high level code, such as VB.NET and C#. We compile it or assemble it into this intermediate format, MISL, and then that's the thing that's actually run. So a .NET program will run quite happily on an Android device or an Apple device, as long as the .NET framework is installed. There's two rings that we use with Intel. So this is Intel x86 hardware. Two rings that we run within on the Intel processor. Ring 0 is the highest level of privilege. It's very difficult to get into that. Windows doesn't have what you could use as a kernel per se, but ring 0 is where all your main core drivers are actually running and highly privileged, and all the rest of this stuff is running out at ring 3. Okay, but more and more, we're really wasting hardware, and we can have a quad core. Even on your phone, you now have quad core. So increasingly, we can run multiple operating systems if we virtualize. So with this, we can run a whole operating system inside VMware, and then we can run our code inside that. So this is more moving towards a cloud type environment. Then if we have a piece of hardware that we want to emulate, we want to debug, it might be an IBM mainframe, or it might be a ZX Spectrum computer, or a Nintendo games computer from the past. We'll typically use an emulator. And an emulator will try and emulate the whole of the device, but it has a massive overhead between the machine code, so something like the Z80 processor in the past as a games processor will have to convert itself into a modern architecture such as the Intel processor. But the place that we see most of the malware happening is here. So most of the malware is now happening through cross-site scripting. So cross-site scripting is that you have a container, you have Flash, Reader, and so on, and then it's running code. The code then drops through the system and then does something onto the hardware. What should happen is that it's sandboxed, so you shouldn't be allowed to get access to the hardware directly. Unfortunately, most developers really struggle with the concept of a sandbox running within a browser and so on. So now Java has no place in browsers. At one time you'd have Java running and it just wasn't trusted. So Java is still a proper language. I think it's in second place, being closely chased by Python. Java is a back-end language. You'll find in many applications it's Java that's used as the back-end, and it's certainly not as a front-end anymore because of the security problems that it caused. Okay, so this is what's as close to a taxonomy as I could I could create. So this isn't from published work at all, but it at least gives you an idea of how we can articulate malware. The major problem that we have in an incident is how we actually articulate in a language that investigators and business people can actually understand. So a malware of a certain classification is distributed by a certain distribution method. So tell me typical distribution methods that would happen within malware. Email, yeah. So that's, yeah, so over email. Anything else? And what would you call that type of attack? Phishing, yeah. Yeah. Any other way? USB, yeah, so leaving a USB. Obviously peer-to-peer sites, downloading software from peer-to-peer sites. There's a well-known Mac exploit for Photoshop where it was called the Mac worm, but it wasn't really a worm. It was a backdoor, and it was to do with people downloading Photoshop for Mac, and the exploit had to put in a little backdoor in it, and then whenever anybody ran it, there was a backdoor. I created them. So there are many different ways, but phishing, the number one security problem in a company, what is it? What are most security problems caused by? People. So the number one distribution method is lack of training. People still click. You hear most companies will say that when they did a phishing exercise in the company, there were still people clicking on the links and putting in user credentials for their cloud account. Then it could obfuscate itself, it could try and hide, it could create, it could have a different packing method, it can have different delivery methods, as we'll see later, through email, but it tries to hide itself, and we still get phishing emails. So even our filtering system doesn't catch them all, and they still get through. 9 a.m. is a really smart time for a piece. 8:55 a.m. is a really optimal time for a targeted phishing attack, because you just log onto your email. The first one you see is this phishing email, and you click on it. So you actually find that a targeted attack will try and get the emails in first before people actually arrive. So there's certain observable events which will compromise the system, and then it wants to live. But some malware now actually resides in memory, and it stays there, and then once you reboot, it's gone. So a lot of servers and a lot of systems will stay up all the time, and a lot of IoT. So quite a few of the most recent malware will actually stay resident in memory, and then when you reboot, they're actually gone. Why would somebody do that?
Most detection. Excuse me. Most detection methods use look on a disk.
Yeah. So for things like SCADA type attacks and so on, it will often be that it will install itself onto the SCADA system and stay active, and then because the SCADA system will stay up and running for years, possibly. So then it can be found through observable events, either in memory, on the disk, the dialbacks it does on the network, and that's then triggered. It triggers an event, and again it tries to hide what it's doing from the virus scanner. I had a statistic that much of the malware that's out there just now for ransomware is not detectable by virus scanners, and almost like every single piece of ransomware is a 0-day type attack. So there's a observable events, there's an attack method that does some damage, and you've got to understand why someone is actually doing something to your company. So it's important to understand the reasons. It's typically that reason. It's typically they want money, and it's a very successful, in terms of ransomware, it's a very successful crime, and companies will pay tens, hundreds of thousands of dollars to release their sensitive information. But we'll cover ransomware in more detail later on. Yep.
So is ransomware actually that significant in a corporate environment? So they don't do proper backups?
For small companies, they have no chance of having backups. For a large company, it might cause an outage of a day or two. I know in the public sector, there was one that it was a 4-day outage. So in a bank, yes, they've got backups. They make sure that there's a cached version of every file. They can afford to pay that. For most companies, they don't have regular backups, especially small companies, especially you as an individual. Do you have backups?
Restored my back for one last week.
Yeah. Because even if
Painful state of bad day, so I've been back there later.
yeah, so it I think most companies. So the public sector is a very good example. It's spread widely, and healthcare. There are so many employees, millions of employees in the NHS, all connecting systems all the time, and it's very difficult, all with phones and devices and.
Oh, the NHS is a nightmare.
Yeah. So there's been quite a few cases of ransomware in the NHS. So I'll give you examples of ransomware later on. For just now, we'll just look at sort of general malware. So it's very difficult to really define a classification so that you can articulate to somebody, this is what this ransomware is about. But roughly they fall into these sort of areas. The kind of older ones, Trojan horses, of course, click on a link, click on this link. There was an example in the Far East of a hotel that executives went to. There was a whole lot of hackers that were waiting for them. They knew the people who were going to the hotel, and then what they did was they just kept pushing malware. It was signed Adobe updates with 512-bit RSA keys. So they managed to push the Adobe updates. You get an Adobe update. It looks as if it's signed by Adobe, but it wasn't. And then once they can compromise the Adobe product, then they can put in backdoors and so on. So Trojan horses, backdoors, ransomware is increasing greatly. There is some sort of exploit that we see within a package. So this is typical now for that. Viruses and then worms. Worms are coming back again. That you'll actually see some ransomware. We'll go and seek network shares. We'll go and seek other machines on the network and then try to compromise them. Facebook was taken down. Everybody know how Facebook was taken down for 4 hours? So it used a malware on, so the creator of CCTV systems, a creator of CCTV systems in China, used the same root password for every single camera that they sold. There was, if you go to shodan.io, you'll see all the cameras. Maybe we can have a look later on, but Shodan will actually show you there's about 500,000 CCTV cameras around the world that use that CCTV system. The malware then went and then compromised each of the CCTV cameras because it knew the username and password. It then targeted the DIN server. So DIN provides the dynamic DNS for Facebook and Twitter and so on. So you don't really have static DNS systems now. Everything's done dynamically on the fly. It'll create new IP addresses and load balance and so on. So 500,000 of these devices decided to do a lookup on Facebook or on DIN for a domain that didn't exist. So it'd be zyf.facebook.com. and DIN got so busy that it couldn't cope with valid requests, and for 4 hours Facebook and a few other cloud services were lost. So the moral of that story is that don't use the same root password on your devices. Every device that we've tested has some root password. You can look at the firmware. You can use binwalk in Kali. Binwalk allows you to look at the firmware, and magically the etc. password or shadow file reveals what the default password is. So make sure that when you're creating your systems that you at least have different ways to authenticate that doesn't involve username and password. So the camera we bought actually had port 23 open. I'll try and bring it along sometime. So we bought a camera and when we did an nmap of it, 23 was open, which is quite worrying because that means that anybody can get into that camera. The default password was, what do you think? 1, 2, 3, 4, 5, 6. And most users would never know that port 23 was dangling. It uses port 80 too, which isn't very good. But port 23 was actually open. With Hydra, it's not too difficult to try different passwords. There's no logging on a camera. You can't go to the log file and see that somebody's been... There was no lockout. Unbelievably, there was no... What you should do is a lockout for a few hours. You're locked down. 4 hours and you're out. Nobody had designed in a lockout. So again, when you're creating systems to defend against Hydra and things like that, make sure you have a lockout after 3 goes to make sure it can't be broken. Okay, so for our static analysis, most companies will use VirusTotal. So VirusTotal is probably the brains of the whole of the internet. Even the big companies use VirusTotal. Whenever they find any malware, it goes up on VirusTotal, and then you get a saint versus sinner thing, and it'll tell you. So it's not guaranteed that VirusTotal will actually define it as malicious, because what is malicious? If an app gets access to my contacts on my iPhone, and it hasn't asked me, is that malicious? It's difficult to know if it asks for my permission, my consent. So we'll typically use VirusTotal, and I'll give you an example. VirusTotal gives you the screenshots that you can actually have a look to see what the malware actually looks like. But it'll give you a signature, but with Packers these days, it's quite difficult to keep up to date with it. But the first thing you should probably do is to get your malware into VirusTotal and then do a quick check just to see what it is. Then you use a hex editor, and with the hex editor you then look through the code, and you'll actually find people can leave their calling card, email addresses can appear inside the code. But what you're trying to do is you're trying to find a specific string or a hex sequence which you can actually apply to Snort or to your virus scanners across the network. So it's really, we either find a string or we find the hex pattern to be able to define our basic signature. And then what we need to do is because static isn't really enough to understand how the malware is working. So we typically run a tool to be able to look at the files that are changed, the processes that are run, the threads, and the registry keys that are modified. So we can actually understand how it runs, what process it starts, and what keys it changes in the registry. Unfortunately, if you've ever looked at the registry, you'll actually find it's forever changing. So we often have to target on the malware itself to see what keys that are going on. And then we obviously run Wireshark to be able to get a trace, a PCAP file of the dial back that it was typically due on the system. So I'll give you an example of an evidence bag later and what that actually looks like. Along with this, we can use something like Tripwire, and we can get a file integrity check where we can hash all the files on a certain subfolder, and then we detect whenever a file is changed by rechecking the hash file. So in this case, we've changed one file, and you can actually see that the system has been able to detect the change because of the change in the hash methods. And then we look at a dynamic payload analysis. So with payload, what we've got is that our lovely virus gets encapsulated into a zip file or a RAR file or a GZ file. It can change its file name, it can pack itself, and so on. So often what we have to do is to look to capture it inside our, in this case, on an email, and then we look into the message, and you can see here, this is what HTTP looks like. It's just a single file, and it has a header, and it has boundaries, and this is the file encapsulation here. So often what we would do for our virus scanner, for Snort, we would grab a bit of the base 64 and we would put that into Snort to be able to detect the malware in the email message. Okay, so remember it's encapsulated, but what's a method that is likely to go undiscovered? So if we have scanners on our network looking for the base 64, what's a guaranteed method to get round Snort? Yeah, you could do that. Yeah, you could pack it. Yeah, but let's say that we know all of the different packings and we've found a signature. So what happens on a Palo Alto firewall is that the code is taken off and run in a sandbox. So there's a sandbox waiting for it, and they pull the code and then they run it. And if it's okay, then they'll let it go. If it's not okay, they might pass it to another level down, which will do a much more deeper analysis of the malware. But what's one method that really Snort struggles with greatly? Still will need to run in some ways. So let's say we do know, and we have a behaviour analysis that we can understand that this is a bad thing.
For embedding sandboxes, sometimes you use a sandbox exhaustion. So you run a really big loop for a long time, and the sandbox timeouts because over time it will lock the system and it passes.
Yeah, that's right. Yeah, so they often have a detector that knows when they're running in VMware or in a virtual environment, and they try and overcome that. That will have a reasonable success rate, but there is one method that completely stumps Snort. And it's the way we're going on the internet. It's the future, but it's a scary future for security. Yeah, it's encrypted. It's encrypted either at the data level, and you're stuffed. If it's encrypted at the very highest level, that's an end-to-end encryption, and there is some way that the key is passed. So a lot of the ransomware now is that it's sending encrypted content, but if it's tunneled through HTTPS, then Snort really struggles to see anything. But luckily, there are firewalls out there that are smart and can break the tunnel and can proxy the tunnel, and they pass the encryption keys on to all the devices on the network from them. So it's solved, but some would say that is breaking the internet. But the internet's kind of broken anyway, so it doesn't really matter. So this is one we'll do in the lab today. So this is an example of the kind of older type Windows malware. It's a malware called the DQ, and we'll have a look at it today. So make sure you're disconnected from the internet. So please, 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 please be ethical in everything that you do with malware. Don't run anything outside a sandbox. Make sure all your network connections are disconnected. So we use Cuckoo. Cuckoo creates a sandbox for you. You have a USB connection to your SATA drive. You put the drive in and you can let the malware run. Cuckoo then creates a log of all the things it's done to the system. You take that off, that's your evidence bag, but don't ever let malware out. So in the lab, make sure you're disconnected from the network, from the internet. Give your network adapter a non-routable address so that it can't get out. So in this case, this is the malware itself, when it's run, puts itself into recycler and then into this folder here. And it's a pretty sneaky place to put it because that's where you put your recycle bin stuff. That's where it gets cleared out. So what it's doing is it's making sure it's in your system and it's in a place that probably won't be detected in there. It's even sneakier that when you do a DIR, it doesn't even appear there. And what it is it's flipped the hidden bit, and it's also flipped the system bit, which is really sneaky. So the hidden bit means that when you're listing it in a normal listing, you won't see it unless you do the AH extension. If it's a system file, it's not easy to delete a system file. I don't know if you've ever tried to do an erase of a system file, but it just doesn't like you to do that at all. So in this case, we can see the malware here. It buries itself in this registry keys here. I know it's difficult to see that there, but this is the startup key in the registry, which will define all the processes that are started up when the computer starts up. So it's difficult to see from there, but basically this runs this file on startup, so every single time. So first, when you're cleaning off malware on a system, first place to look is here and get it out of the startup. So at least when you boot it back up, it's not going to come back again from there. Okay, so we'll do that in the lab today. Then you get deep down. So IDE Pro, we've got a couple of licenses here. It's a very expensive package, but it can do everything that you really need from it. So with IDE Pro, we actually get right into the code, and we can look at the stacks and the code running and what it's actually doing onto the system. So I think we'll be doing some analysis of this kind of thing in the next couple of weeks or so. 64-bit, yeah, with IDE Pro, that's right, yeah. It is an expensive package, but it's extremely powerful. So normally what we do is that we get some code analysis. I'm just showing Visual Studio here, but you might use your Xcode for the Mac or whatever debugger that you want to use. So the debugger will often show you memory, the code disassembled. So this will show you what your code is, what your code reverses back as, show you registers, and then also your stack. So this is what our code looks like. So this is our machine code format here. So this is the machine code, and this is the assembly image that's generated from it. So all the computer understands is these codes, which become binary. We don't speak binary, so we have to convert them to hexadecimal. So when the code runs, it starts off, and then it just runs, and it might jump, and then it will move back and forward reading these commands. Okay, so to show you an example, int a equals 1, how we do that is we move the value into, does anybody know what square brackets mean?
Should be a reference to the memory address.
To the memory address, yeah. So it's called a pointer in memory, then there'll be an address location called A, and the value of 1 will go into that memory location, okay? The processor sits and it has scratch areas called, what would you call your scratch area in a processor? Got a bit of scratch memory. What is it? No, that's another thing. It's registers. So it's got some registers that it's using to do some stuff with. Everything it does is with a kind of, and it's usually with registers, fetch, execute type thing. Okay, so we can see we're moving the value of 1 into wherever A is, we're moving the value of 2 into wherever B is, and that loads up the values here. And when we add two numbers together, we take what's in the contents of A and put it into the EAX register. What's the difference between EAX and AX? I'll explain it in a little minute. But AX is 32 bits and EAX is 64 bits. So that's when a program's running in 64-bit mode, its registers are a lot bigger. If it's running in compatibility mode, it's running 32-bit registers, and even you can get 8 bits. That was AH and AL. So we put A into EX, and then we add on the contents that's in AEX with the contents of B. So what will the value of EAX be before we execute this statement here? What was it? A, which is 1. And now execute, and the value of EAX will be, what was it? 3, okay? And what I do here is I take what's in the EAX register and I put it into the memory location pointed to by Z, okay? And that's the way that the code works. So those are some of the codes that we use. We move from registers into memory and vice versa. Interrupt, we interrupt the computer when somebody presses a key. We create an interrupt, we handle the interrupt, and we come back. What we've got to do in the interrupt is to make sure that when it comes back, everything is just as we had it before. So we have the concept of the stack, as you say. The stack is where we put all our variables. If we've just been interrupted by the user pressing a key, we stick all our values or our registers up onto the stack. We do the code, and then we come back and we take all the stuff back off the stack, and it's as if we had never left our code. Push allows us to push onto the stack, and it's a bit like when you have your coins, when you store your pound coins, you push and you pop. So it's a first in, is it first in, last out? Last in, first out. I would call it first, yeah, last in, first out, that's it. Last in, first out. FIFO. First in, no, that's wrong. you pop them back off in the reverse order. I'll explain it in a little minute. It's like when you have the coins and you push the coins in and you take the coins back off again. That's what push and pop do. Calls a function and returns back from it. From there, we can compare. So what a cracker typically does in a piece of code, if there's a place where it checks the license, they go and change the hex code. So if it's a jump if equal, they'll make it have a jump if not equal to. So it's very difficult to really stop somebody from flipping bits and changing the code in the program. Okay, so that's what our code actually looks like from there. And unfortunately for malware, you've actually sometimes really got into the detail of what's going on at the machine level. And the more we move towards IoT, the more we move towards the simple devices, the more we need to understand the machine level coding. So here we go here. The registers that we have here are these ones. AX is a general purpose register. We have our code pointer. So our instruction pointer is here, and it's telling us where we should be at any given time. So we'll be jumping about. The program, the instruction pointer, actually tells us where we should be going next. So we see here when we're running the code, what we're seeing is the instruction pointer here is showing us the next place that we should go, and then here the next place is C, and then so on. So the instruction pointer is changing all the time. If we do a jump, then we'll see that changing from there. So in this debugger here, the red is highlighting. We typically step through the program one line at a time. We put a breakpoint, and then we step, I think on Visual Studio it's F8 or F10, and we step through one line at a time. We can decide if there's a jump, whether we just jump over the function and go into the next part, or we can go into the function there. Okay, so this is what the processor looks like. These are our registers. We have what's called a code area, and we use von Neumann, which means that code and data share the same space, roughly. It didn't have to be like that, but that's the way that they created a computer, that we just have a whole lot of memory, and horribly, we actually have a place where we write code and data, which causes horrendous problems. So what problem does that type of system cause for security? Could be. We'd know roughly what was the code area. We do segment the areas when we're running. It's not. Yeah. Yeah. Yeah, I mean that's the problem, but there's a bigger one that causes most vulnerabilities. Yeah, so code can the data area can overflow into other areas. So the so those are our registers that we have in there. So there's our simple program. Here's a call to a function, and we're calling a function called add. And what we do is we push the values of the registers because we want them to return back as they were. So what we've done here is that we push those two registers onto the stack, and then at the end of it, we'll be popping them back off for our code. Okay, so there's a processor, there's a memory, we have a data bus. How big is the data bus? On a normal processor. Was it? Yeah, 64. Yeah. Then we have our address bus. We put an address on the address bus. It points to place, and then we read or we write. That's the way the operation happens. Okay. There's a stack pointer that shows us where the stack actually is, and the instruction pointer shows where we are in the code at any given time from there. Okay, and we're pushing and popping. This can cause real problems, especially with memory leakage and things like that. We can also do a forensics analysis. So if we're looking at the code, we identify, typically from a magic number, what we're dealing with, and then we go and pull out the spec for that format. So most of the formats will be fairly well defined in terms of what comes later. The magic number allows us to find it. If I have a graphic file, say a JPEG, do I only find that? Well, I only find that header. So let's say we go for PDF. Okay, that's the magic number for a PDF file. It's the only place I'll ever find on the disk that sequence when I have a PDF document. No, why not? Well, PDF is often encapsulated in other formats, and the same with PNG is. So in something like a Photoshop document, you'll often find PDF tags in there. So you find PDFs all over the place in PNGs and JPEGs, but they're not actually files. They're within other files. So they're encapsulated inside other ones. So what we'll often do is to be able to look for our magic number. And I've got a page that lists virtually every magic number if you're interested. And then what we do is that we then find the magic number, and then we've got to look at the spec that will actually define the format that happens after it. With an MP3, it becomes a bit difficult. You look for 11 ones is the standard sign of audio from there. Okay, so the spec actually defines what the format is and how you should interpret the part that comes after that. So in terms of malware creation, malware creation can be done through something like MSF Venom, which will inject the extra payload that's required for the code. So what it tries to do is to be able to take this part here and add it into a standard exe to make sure that the actual code looks valid, but what it has is a backdoor. When the user runs putty X, it still runs putty, but then it opens up a backdoor for the intruder to get into the machine. It does a dial back. Most of the malware you don't contact, you wait for the dial back to happen, because most people will sit behind NAT. Okay, and this is the exe here, this is the injection of the code. Okay, so this is taking the putty code, and you actually see that the payload that Metasploit, the payload that MSF Venom has added is in one of these files. And if you look down, that you see the payload defined for Metasploit there. And then when you look at the binary analysis, when you look at the binary analysis, you actually see it within the exe here. The exe will get bigger typically, but what will change in the exe? How could you stop this from happening? How could you stop running a backdoor program like this? So normally we'd create a hash, and when we download the program, we check the hash. So when we download it, we check that the hash, as long as we trust the site and it has been compromised, we rerun the hash and it will create a completely different hash. But it's not too difficult for these byte stuffing programs to end up with the same hash value than we have here. So don't trust that.
With respect of offering the hash, things that if you are able to reach to an official site and upload backdoor software, you are also able to access that hash and modify it, right?
That's right, yeah. So somebody could have compromised the site.
And
yeah.
if the program is corrupted, the person that corrupted the program has also access to that hash.
Luckily, most of the virus scanners actually know about Metasploit and know exactly all the standard ones, so they know the payloads that are there. So it's very unlikely that they'll get away with it. If you're running a Mac, your exe isn't going to work anyway. I mean, the Mac, Linux is now the top for vulnerabilities now. For the first time ever, Linux has taken over from Windows, and Mac and iPhone and Android are the targets now, and Windows less, because it tends to be a bit more secure now. These ones, anything that Metasploit has, the virus scanner will actually know it, and will know the behaviour of a dial back. So I wouldn't expect you to read this and know what's going on, but this is a real exploit kit. That's what it looks like. That's what you buy. The ones I've got here, this is for Flash. This is the compromise file here, and it allows a backdoor into there. It allows the JavaScript to run in the Flash version. This one here is the action script for Flash. So this is the JavaScript that runs the Flash, and this is action script is what runs inside a Flash movie from there. So these cover these exploits, and typically it's a memory compromise that happens. Right. So in this part of the lecture, I'll give a few demos of using the of how we can use Metasploit to be able to inject the code to do dial back. So the dial back needs to happen because the user will be the target will be sitting behind that. It's very difficult to make a connection. So the connection is made from the target device. Okay, so what I've done is I've created a few exploits with MSF Venom. I've put it onto the Windows machine, and I've also created an APK. So MSF Venom will create whatever architecture that you want. So if it's this one, if it's Android, then it's for ARM architecture. Apple is a bit more closed in terms. They will look at the code that's uploaded onto the Apple Store and make sure it doesn't have any backdoors or malicious things, and they're getting stricter if anything. What we found in our research here, it was from an MSc student from last year, is there's a whole lot of Android sites with APK malware on them. So just watch if you're using an open store for your Android device and you aren't going to Google Live. But even if you lose Google Live, there's no guarantee that what you're downloading doesn't actually have a backdoor. And some people, a backdoor is that somebody's actually spying on your contacts lists. You might have not read the permissions, but they're actually having a look. I know that a lot of applications do that now. So it isn't just a malware backdoor that someone might apply. Okay, so I've got set up here. So you can have it there. Okay, so I've got a Windows machine that I've set up. So I've got a number of programs on there. Let's see if I can get this plugged into something. It's a bit better. Okay, so then I've got Metasploit set up. So this is it's just a simple compromise here. So all that's going to happen is it's just going to do a reverse shell whenever the user runs the program. Okay, so if you go and run the first one now, it's not the easiest computer to use. This one, yeah, that's right. Yeah, so just double click. Okay, so all this one is a reverse to be able to look at the files on the system. So look at Windows, and there's system 32, and so on. So the user would never know that there was someone actually sitting on the machine. So the second one is a VNC inject. So with this one, a machine can run a remote desktop, but will typically not, or you may need licenses for it. So in this case, Metasploit will actually deliver a full VNC server to the device as a payload, and then run it and then create the dialback so that we get remote access onto the machine. Okay, so if you're on the second one. Okay, so it's fine. So what it's doing now is it's downloading it's uploading the payload to the target machine. Okay, and so if you just double click on hello.
Hello?
Hello, yeah. And just open it up. There we go. Okay, and then just close it. Okay, and the user would never know that they were actually on the machine at this time. But then what we can do is we can install the interpreter, which gives us many more commands that we can use. Like that. Okay, so now run the third one, please. Okay, so now the interpreter gives us a whole lot of commands. We can get the system now. Might be obfuscated. Well, what we can do from here is there is a way to hook on to a service which is running at administrator level, and to be able to get the privilege from that. But what we'll do is we'll just have a look at the webcam list. So there's one webcam on there. Oops. That's not webcam left. So it's to find snap. Okay. I don't know what that's taken there, if it's taken a picture. Maybe a bit dark for the picture. Oh, it's you. But then what we can do is we can stream from the webcam.
Is this how people put up those private streams and stuff like that? Hit the camera?
Go on, wave. That's good. A wee bit of a lag. Go on, wave. And the snow, it's not really snowing, is it? Very, very much.
I've got a question. See, it's all fine sending these in an email and stuff and having the hook set up, but how would you be able to connect to someone's network? Let's say I sent an email out to someone in London or down in Germany, and then I had this set up on my computer. How would I be able to get that back?
Yeah. Can we talk about this after the cameras are off? In the lab, okay, we'll talk about that. So obviously what can happen is that somebody can send you an EXE. These were just EXEs. So a typical one was that the chief executive has a PA. The PA looks after all their work rather than contact the chief executive directly. They contact the CA to say that the chief executive's child has fallen at school, but it's okay. Here are the procedure that you should do to be able to make sure that everything's fine. The PA clicks on the EXE or the PDF because she panics, and then it drops a backdoor onto the machine. So people really are still clicking on links, but obviously there are other ways. Okay, so that's everybody knows that Windows isn't really a very good system in some cases for coping with malware. So in this case, what I've done is I've created an APK and installed it onto my Android device. I've got to come out with my interpreter. Well, there's a whole lot of, as you probably know, there's a whole lot of other commands that we can use. We can capture the microphone, and we can capture the key scans and so on. So if we just come out of the interpreter and get back into there. That's fine. Okay, so this is my Android device, and what I've done is I've installed an APK on it. An APK is just a Java file. Google created their own Java version, much to the displeasure of Oracle. And I've got just a little program here. You can see the little Android one here.
Yeah.
It's okay. So just click on the little Android guy. Oh, good. Right. So that's created a connection here, and I can have multiple. This is session 5 here. So now I've got the same command set that we had before, and what we'll do is we'll just take a snap again. We've got 2 cameras this time, so I don't know which one we're going to be taken from. That one looks like the other one, so we'll take it from the other one. Oh, that's taking you. Yes. Okay, and then we can do our webcam capture there. A stream, yeah. So there's no light. There's no light. Oh, sorry. Where are we? Over here. So there's no light there, so you can't really tell that it's actually on just now. But just to show it as real time, that's right. It's not quite as fast. There we go. That's an infinite loop, I think, is it? I don't know. Cameraman. That's it. Cameraman. Oh, so I've lost you. There you go. I got you. So that required a piece of malware, but it isn't always the case that you require a piece of malware on it. So this next one was a Google. Google don't patch very often, and there's 1 billion phones out there. Oracle tried to sue Google because they took the Java infrastructure, they copied it, and created their own virtual machine. And Oracle wanted, imagine getting even a small amount of money for every device that's sold. It didn't work because it's what it's how the IBM PC got hacked. That Compaq didn't take the BIOS, which made the computer work. They recreated their own BIOS with new source code. If they'd copied it, then it would have stopped, as many did at the time. So Google doesn't patch that often, and this one was running wild for about a year, and it's still probably vulnerable on millions of devices across the world. So just because your Android phone gets the latest updates from 3G and so on, doesn't mean if you go around the world that everybody's networks are going to be the same. So this exploit here uses an exploit in the web, the JavaScript interface, and all it requires is a contact with a web server. So all it requires is a promise is to visit a certain website that's running the exploit, and just let me see what it is. That's fine. So just let me bring up the browser on the device. And then I'm going to connect to 192.168.0.24. Can you just check that that's okay? 192.168.0.24. And so I didn't do anything. Honestly, there's no malware here at all. This is purely a bug in the Android system, which went unpatched for quite a while. It just takes a little minute. Hopefully we'll get there. Okay, so it's created session. It's created a session. It's created session number 6. So with Metasploit, we can sit having lots of sessions open, and then we can just go back to them. So we went to session 6, and now there. So I don't know if you see the subtlety of what happened there. This is purely from a web browser, and there is no malware installed on it. And this was running wild, and still is on many machines, just to show that it does work. Try it from the second camera. That's fine. Oh, sorry about that. There you go.
That's it.
That's it. A green Mac. That's really good. Okay, so that last one really scares me completely because there's not much you can do about it than actually patch your machine. Oh, see that. Okay, so we'll be doing a bit more on that coming up. That's the movie. Okay, so what I'd like to do is to show you how easy it is for users to be tricked. So even I get tricked, but I click on every single phishing email. I do check, and I do take precautions. But I'll show you some of the methods that they actually use within Cythium. So a typical one they'll do is hook onto something that's current. Like here's the Trump inauguration. This is a new video, or here is the X Factor winner, something. And if it's targeted, they know exactly what you like, and they will maybe use your next of kin or something. If it's so targeted, if you're employed to target somebody, then you do the due diligence and so on, and it can be targeted. So this was an example of one that was around. So this was there's an outbreak. There was when Ebola was around. People panicked. They wanted to see the details, and they opened up their RAR. Once they did that, then their machine was then compromised. So this is one that tricks many people. And when does it happen? It happens in January in the UK, and they're just blasted. So they screen scrape all the graphics from the proper website. Everything that they have in here is actually taken from the real sites. You'll see, it's difficult to see here, but you actually see the graphics are coming in from hmrc.gov.uk. So they're not even hosting those files. Those files are coming in from the HMRC site, and the fonts, the style sheet is purely from their site. So everything looks to be completely valid. You then go ahead, you put in your details, and then what tag do you look for? What's the magic tag that you would look for in your HTML to find out where it goes?
The submit.
What is it?
The submit. That is the
Submit.
main- yeah,
That's right, but
main post.
submit is where it goes. But there's a couple of tags. There's a tag that's used to encapsulate what happens with the submit button.
Post.
Was it?
Post.
No, it does a post. Yeah,
The post method.
there's a post method. No, nearly. No, it's the form. Just search for form, and whatever's encapsulated in the form gets sent through as variables. Whatever's in your text. Is that right? Yeah.
Yeah.
Good. So this was the one. This one here. Let me disconnect. So everything I did earlier was on my own private Wi-Fi. Okay, there was no connection to the internet or anything like that. I promise. So when you're doing demos like that, make sure that you're not using any public Wi-Fi and so on. Okay, so this is an example here. So this is you can see your Barclays Bank coming through here. When we look at the HTML of the email, you actually find out that the link here goes to an incorrect site. So that's what Barclays should look like. And you should always make sure that you have a certificate for it. So that's the valid one here. Okay, when we roll over the link here, then you can see it goes to a non-Barclays site. We then look at the header of the email. So this is where we reveal who sent the email, where it came from, when it was sent, and so on. So it's in here that we can actually discover that the email really wasn't from Barclays, but it was from some other non-trusted site. Hopefully, if you've got your email set up, it will detect that this is a Barclays Bank email, and actually the relayer isn't in there. So this will tell you where it came from, what the address was for the sender. So you see there's a received from. I know it's difficult to see it, but there's a received from, and it'll tell you the email really that actually sent the email out. And if it's valid, it should be coming from a valid looking site. Try and find it. Okay. Okay, so when you actually go to the site, they've obviously used the Barclays logo here, but you can see at the top that really the site itself has very little to do with Barclays. Okay, so here's another one with an HTML. So the HTML, you just click on the HTML, and we get a form which is obviously running locally on it. Okay, so you put in all your details, which obviously you wouldn't. And you go to submit, and you've lost your login details. So what we look for is that we scan down until we find the form tag. And we within the form tag, we actually can determine the parameters that are actually sent. In there. Stretch out like that. It's a bit difficult to see, but here we see the form tag, and as you said, there's the action, and the action is posting to a PHP script. So all of the parameters that we are setting in here, email, and so on, those parameters get sent into the PHP script whenever you do your post. And it's very difficult for the user to really know that that's actually happening. Okay, so I'm just going back then. Okay, so this is one I got recently. So I was worried because I had taken a subscription for Netflix, and this came in. It had the proper Apple logo. Everything was fine, and it looked like it was a proper invoice. But when you see the refund, the only thing in here that gives the pointer to that is that goes to a site which obviously isn't Apple. Okay, so you'll see there that everything about that email is coming in from Apple. The logos are from the Apple site. Everything's fine there. But when you click on the refund, okay, so when you click on all the other links, they're fine. If you go to iTunes, it will take you to the Apple site. But obviously when you click on here, it goes to this site here. Again, this is PHP. You really got to worry. There's no certificate on this at all. And so this is what you get. And the telltale signs is that all these links are fine and will take you to a proper Apple site, but this is actually a graphic and you can't select any of the text. I don't know why, it's just cheap. But this is a graphic and you can't select anything there. The other thing is that this says password. I don't know. They need a spell checker. They need a spell checker or something, but they didn't get through there. Okay, so if you put your Apple ID and your password, really, you might not get your money back. Okay, honestly, you think that you're safe online. If you've been stupid and put your password where it says password, and then you will not get your money back. So watch it. The form tags again, so the form here, and hopefully a bit further up. When we this form is okay, but it's this one down there. See, there's this one down here. Login.php, iTunes here. See this is going to their site and not to an Apple. So the tag in there, and it's even got a little tracker on you. So whenever you see a phishing email and there's a tracker on it, don't click on that. But they can put a 1 pixel graphic, and the graphic, they just watch on their server. They know when you've opened an email because there's 1 pixel. They download it, and the pixel has an ID on it. When it does a post, they've said, yeah, you're alive. A lot of them just want to know that you're alive. Luckily, with the EU regulations coming along, it's going to be really highly illegal to do that kind of stuff. But that happened with cookies, and it's never quite went anywhere. Okay, so the code itself was posting the details of the user from there. Okay, so some of the things, like anything that asks for a username and password in an email, is really quite bad. Graphics used instead of text is one way that they get over the scanning. Poorly laid out content, bad spelling. An IP address is a web link instead of a domain name. Domain link that differs from the domain. The graphics content taken from the external site. And then iframes. So iframes allows a perfectly valid site to hold malicious content. So it happened with eBay. There was a code injection. There was an iframe thing that happened in the page on eBay, and a malicious person could send you an email, and it would inject code into the iframe, and then we did a post. Then the details went to another site. Okay, and this is what they do. Can anybody read that? This is perfectly valid code. Okay, I love getting these, and I love running the code in the end. So this run, I can assure you. So this is what they do, and this is the techniques that they use. So this one here, what's that? It's hex. It's a hex code. This one is a Unicode, 16 bits. This one here is a decimal code. This says keystring. This string here says the word keystring, because 137 in decimal. Okay, so this is what they do. So they take, there's the encoding here, and this is what the actual result is, and they're using several different ways to be able to encode from there, the Unicode, the decimal code, the hex code, all which will give us back the character. I can't remember, so if we make that 6C, convert from string, that's there. Okay, so that's the methods that they use there. So you can see that they've encoded all the strings in JavaScript to make it difficult for you. So all that does is produce this string from character code, and that the target is to get under the scanner. When you actually end up and you run through the code, it actually builds up the JavaScript. So the code that we've seen before, that when you run it, actually becomes that. Okay, all they're doing is they're just detecting what type of browser that you've got from there. And there, remember at school you were told, like, your variable names, make them nice names. The code will often be A5, B10, and it obfuscates it even more. Okay, so there's another example there. So this one I received. It's quite interesting. It's a county court order, and you go, oh dear, that's really bad. When you open up the zip file, you get that. Can anybody read? No. And you see, surely that doesn't run at all. But it actually does. And so the code that you actually end up with is this one. So when you split it out and you start to put line breaks, so line breaks are good because you can start to see. So what they do normally is to crunch it all in together, so it's very difficult to read the code. But when you actually start to break it out, you can actually see there are a whole lot of functions being defined. Then there's a bit of code that says from 1 to 237, run that. And all it does is it then runs this function, that one, and that one. So it's packed them, shuffled them up, so that you're totally mangled. But the code itself, all it's really doing is func on DL F DL FR V there. So this is the start of the code, and then it'll write out what the JavaScript actually is. If you keep interpreting the code, this is what it comes out as. And you can see straight away with the website that's actually causing this in here. Okay, so you can see some of the methods that they will use to completely scramble the code from it. And then if you actually go, we've got this as a lab example later. You can then capture the Wireshark trace as that script executes. Okay, so one last thing. This is the vulnerability that I demoed, the last demo that I did on the Android device. This was the vulnerability here, and it affected all versions before 4.4. And I think recently, you can see we're up to about here, and there was a fair percentage of the devices in the world which were using Jelly Bean and Ice Cream Sandwich that were vulnerable to this attack. Okay, so that's been an introduction to malware. What we'll do in the lab today is a little bit of Windows malware and actually see the operation of it. Does anybody have any questions?